All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be learning about Tokyo. In my case, I'm going to be continuing learning about Tokyo because I started learning yesterday. So, after yesterday's stream, where we were reading up on, the conversations that I had with Gemini about, let's see, about auto agents and then Ractor, and then that eventually led to Tokyo. After that conversation and after that stream, I decided to wait. Give me a second. Sorry, give me a second here. I just need to open up my stream on my phone so that I can see my chat. Uh, right, great, awesome. So after yesterday's stream, I created a prompt and I asked Gemini to basically become my tutor for teaching me Tokyo. Uh, Hold on. Let me show you guys this thing. Actually, I I think I would have an easier time scrolling up if I was doing it through here. Yeah, so I can show you guys going all the way up here. Where was it? This was the prompt. I said, you are a tutor. You are going to teach me all about the Tokyo crate slash framework in Rust. Start by creating a syllabus, print out the syllabus in your next response so I can see it. Additionally, serialize the syllabus to JSON and TOML. This was just for my curiosity to see what the syllabus would look like in TOML form, because I do want to start working with TOML as well. I don't want to just stick to JSON because there are quite a few situations where I've seen TOML being used. So I feel like I could benefit from it as well. I feel like I could use TOML in my own projects as well. But yeah, carrying on. Where was I? Yeah, serialize the syllabus to JSON and TOML and write the data to so and so files respectively. Aside from this, aside from this one write operation, I do not want you to perform any other write operations unless I ask you to. If something needs doing, let me know and I'll do it myself so I can learn. Once this is done, let me know and we can start learning. I meant to say learning there. We can start learning from the beginning. For each chapter, I would like you to give me a small exercise at the end of the chapter so I can practice and learn. Just for your info, I know the basics of Rust. I haven't gone into more advanced topics like lifetimes, smart pointers, concurrency, and FFI. This is mostly true. Not entirely true because I have explored the concept of lifetimes. I don't fully understand it, or rather, I haven't practiced lifetimes in all situations. I've practiced lifetimes in something like functions, for example, but lifetimes get used in a bunch of other situations as well. So I haven't practiced lifetimes. I haven't learned lifetimes in like all situations. So that's why I just didn't want to say that I have learned anything about lifetimes at all. And then smart pointers, I have played around with box and ref cell, and I think I've played around with RC. I can't remember. I did use box or ref cell, one of these two. But like, I still feel like I'm relatively new to it, so I don't want to say that, hey, I know this thing, because I don't want Gemini to end up using one of those features in the examples that it or in the exercises that it creates for me, because then that's gonna add complexity for me. Then what else? What else? Hold on. Concurrency. Yeah, concurrency is that's true. I know nothing about concurrency in Rust. I haven't touched that topic yet. I haven't gone into threads or mutex or whatever other multi-threading related concepts in Rust. Um, and FFI as well, I've just not touched that topic at all. So I wanted to be upfront about, what I do and don't know, so that when Gemini is creating examples for me, it'll create the examples using concepts that I do know, not concepts that I'm not familiar with yet. Okay, then I said I'll get there eventually, but in the meantime, if possible, teach me, keeping in mind that my Rust knowledge is limited. Okay, cool. So that was my prompt. Gemini said, of course, I will create a syllabus tailored to your experience level, focusing on the core concepts of Tokio without getting too deep into advanced Rust topics initially. We'll introduce concepts like arc and mutex as needed and explain their roles in an async context. Here's the syllabus I've prepared. I've also written it to so and so and so and so in the current directory. So this was a syllabus that was prepared. Fortunately, it's only 7 chapters. It's not very long, so we should be done with this. Hopefully, we should be done with this relatively quick. I'm hoping maybe it's the next couple of days, because learning Tokio, I'm actually going to be using Tokio in a bunch of other situations as well. So if I'm getting the chance to learn Tokio right now, then I should take that chance and learn it, so I can apply async and actually multi-threaded programming as well. Like, something that I should do research on is, if we have something like Tokio already, then what would be the benefit of doing of writing the multi-threaded code by hand, if that makes sense? As in, there's a bunch of multi-threading there's a bunch of the multi-threading aspect that gets handled by the Tokio runtime itself, because the Tokio runtime handles the handling of the various tasks, and the Tokio runtime is responsible for managing the threads that are going to be executing these tasks, that are going to be doing these executing these tasks. And the Tokyo runtime also implements that whole work stealing feature, where one thread can take jobs from another thread if the thread is actually available to do jobs right now. Where was I going with this? Yeah, so I need to do research on what would be the benefit of, or what would be a situation where I would need to write multi-threaded code by hand as opposed to using something like Tokio. In fact, maybe I should do that right now. I could open it up here. Wait, should I open it up here or should I open it up over here? Okay, you know what? We can do it here. Learning Tokyo. Which one is this? Um, I don't think it's supposed to be this one. Okay, let's open this up, and while that's opening up, we can continue here. So this is the syllabus. Okay. Chapter 1 is the foundations of async and Tokyo. I think it initially, like, it dove into async, the concept of async programming in Rust, and then it went into what exactly Tokyo is. And that's something I really liked. I'm really considering exporting this entire conversation and like posting it somewhere. Um, I don't know. I'll see. Actually, I kind of want to export it. I kind of want to export it in both Markdown and JSON format, and then put it up on GitHub, just in case it could benefit someone. I'm gonna have to clean up some of the conversation here, because there's certain things that I don't really want showing up. And I mean, not because it's something personal, but like, just stuff like, for example, oh, I wrote so and so thing to so and so file, or stuff like that. That doesn't need to be shown. Or maybe I could show it. I'll see. I'll see. Um, Yeah, where was I? I was saying, yeah, okay. So then chapter two, this is where we actually start, doing stuff with Tokyo. We are currently in chapter two, I believe. Yeah, we are currently in chapter two. I'm done with chapter one already. And this is why I was saying that I'm already a little ways into it. I'm not starting all the way from the beginning. Then we have chapter three, which is communicating between tasks. Now, with chapter two, we are actually spawning tasks in order to do work concurrently. And then in chapter three, we're going to be communicating between tasks. Chapter four is handling asynchronous I/O. I'm guessing that's basically when we have to like wait for for an action to complete. So then in the meantime, we can go and do something else. Then we have time and delays, pausing tasks with so and so, and setting timeouts for operations with so and so. Running code periodically. Oh, okay, that's interesting. I didn't know that was an option as well. Okay, cool. Uh, then managing multiple futures, the challenge of waiting for one of many events. Then using select macro to erase multiple futures. And then there's an exercise. And finally, there's a mini project that's going to use all of the concepts that we have learned. That's chapter seven, where we're going to build a project out of the all of the concepts that we've learned in the previous six chapters. Right. So I'm done with chapter one. Now we are supposed to go to chapter two, which is um, just a second. That's here. Okay. So here I was in this section, which is spawn. Right. So the primary way to create and run a new independent asynchronous. Actually, I should be reading it here. Wait, give me a second. Yeah. Okay. So then I can do the typing here. Okay. The primary way to create. Wait, just a second. Okay. The primary way to create and run a new independent asynchronous task in Tokio is using Tokio spawn. This function takes a future, which is an async block, or an async function, which is what? Which is what an async block or async function returns, and schedules it to be run by the Tokio runtime. Okay, the syntax looks like this. Okay, cool, great. Then when Tokio spawn is called, the provided async block immediately becomes a future that the Tokio runtime starts executing alongside other tasks. The spawn call itself is non-blocking. It returns almost instantly, even if the new task takes a long time to complete. Okay. Then using join handle to wait for a task to complete. When you call Tokio spawn, it returns a join handle where T is the type of the value that the spawned task will eventually return. The join handle itself is a future. This means that you can await a join handle. Oh, okay, so that's how we should go. I was actually wondering how do we tie this back into the main function? Like how exactly are we meant to be using it? And I was just going to do something as simple as, running Tokyo spawn directly within main. But here there's a slightly more sophisticated way of doing that. And this is actually probably the right way of doing it. Okay, so this means you can await a join handle to wait for the spawn task to complete and retrieve its results. If the spawn task panics, awaiting its join handle will also propagate the panic to the awaiting task. Okay, all right. Then, okay, hold on just a second here. Oh, you know what? Also, there's something that I might need to change. I don't know if any of the other images are already. Nope, that's not the one. And is this the one maybe? No, that's Kaggle. So here I need to select Rust because, today's stream is Rust. I was going to leave it as Python, but then since we are actually doing Rust, so might as well have the right logo. Um, right. Okay, great. We can probably bring it up here. It's not gonna harm. Great. Awesome. Okay, going back to this. So this is our example. This is our main function. In the main function, we first create a handle, and then we sleep just to sort of simulate other work, and then we await the spawn task's completion and get its result. Okay, we can try doing this. In this example, the main function doesn't block entirely while the spawn task is running. It can do other work before eventually waiting for the spawn task's result. This is the essence of concurrent execution in Tokio. You know what? Let's try doing this. I'm still fairly new uh, to to doing async programming in Rust. So it's gonna take me a little bit. So okay, right. So we do that. Then the function needs to be async as well. Async fn. Why is it all replacing, dude? What? Async fn main. Okay. So that's done. Now we create a handle. So let handle, wrong handle, let handle join handle of type U8 in this case equals Tokio spawn, and in here we want to pass in async okay. So print line task starting. Okay, then this task is also sleeping, so this is just simulating something that takes time. So task.sleep time, task.time dot sleep. And then here we want duration from seconds, 1 second dot await. And finally, oh wait, no, there's another print line. Task finished. And then finally we return this. Right, so then we do print line main function doing other work, and then we do the sleep thing again. Time, sleep, and this time it is from milliseconds. So duration, sleep, no, duration from milliseconds, that's 100, so that's what, 0.1 second? How many, does 1 second have 1,000 milliseconds, I think? Give me a second. Um, Milliseconds to seconds. Yeah, I would say it's 1,000. Yeah, okay. So that's point 1 second. And then we are doing await here as well. Right, then we get the result using handle.await. Wait, that's interesting. Why is that not working here? Is there like an error or something? Okay, let's do it anyways and see what. Okay, that is odd, but it works. Okay, cool. And then expect. Okay, I'm still not sure if it works. Task panicked. Okay, all right. Then print line, spawned task returned. Result. Okay, cool. So we can run this using, wait, there's a mistake here. What's the mistake? Mismatch types. Join handle integer and so have similar names but are actually distinct types. Why is there an issue with that? Oh, is it because of this? Should I do something like this instead? Tokio task, Tokio thread. Oh, wait a minute. Join handle. Oh, it picked up right, hold on. I need to, so let's do use Tokio, join handle. Where does join handle come in? Wait, hold on. Mismatch types. Thread, okay. Task, okay, it's task join handle. Task join handle, and then here it is time duration. Does that solve the problem? Yes, it does. Great. It was an issue of ambiguity, and I'm guessing that's also, just a second, that's probably also why this await issue was occurring. Let's say I Okay, we reconnect. Oh my God, dude. Are we back on? I'm not sure if we are back on. I think we're back on. Yeah, okay, so we disconnected um, briefly and then we reconnected again. Anyways, okay, so let's rerun this. Task starting, task finished. Okay, great. So, oh, that's an issue. Give me a second to solve this little problem because we just had a disconnection. Dude, I think I need to replace this router, dude. Okay. Um, yeah, let me just do the connection thing again. Okay. Where's the tmux thing? Okay, whatever. Let's attach to temp rust, and I think we are good now. Okay, great. So that was the example. And now we can go further down here. Okay, in this example, the main function doesn't block entirely while the spawn task is running. It can do other work before eventually waiting for the spawn task's result. This is the essence of concurrent execution in Tokio. Give me a second. Let me just make sure I have some background sound. Okay. Okay, now on to the exercise, which is your goal for this exercise is to demonstrate the concurrent nature of Tokio tasks by spawning multiple tasks that run in parallel or interleaved by the runtime. Modify your main RS from the previous exercise. Keep the Tokio dependency. Okay, implement the following. In your main async function, spawn at least 3 different tasks using spawn. Okay, each task should print a message indicating which task it is. Example, task 1 starting. Okay, then use the sleep method for a different duration. Then print a message indicating it's done, and optionally return a simple value from each task. Collect the join handles for each spawn task. Okay, what more does it say? Is there a 3? Oh, wait, there's more. Okay, after spawning all the tasks, print a message from main indicating that all the tasks have been launched. Then await all the join handles in main and ensure all tasks complete before main exits. Print the results returned by each task. Expected output may vary slightly due to scheduling. Okay, this exercise will clearly show how the Tokio runtime interleaves the execution of your tasks. The finished messages should appear in an order determined by their sleep durations, not necessarily the order they were spawned. Let me know once you've completed this exercise and are ready to move. to move on to chapter 3. So, okay, in this chapter, we've learned about join handles and also how to, of course, spawn a task. But we've learned about join handles. Just a second. Okay. All right. So what we could do is, what was the thing to go to the end of the function? Yeah, I'm curious about that because like, okay, this, oh, maybe it's because there aren't multiple functions. Right. Okay. So in here, what do they want us to do? There's, wait, actually, let me come back here so we can show all of this. Okay, great. So, in your async function, spawn at least 3 different tasks. Okay, so let's do task O1 equals, I'm just going to let it infer. Hold on, can I just import the spawn function here? Okay, spawn async, and then this and that. Okay, so probably the first thing we want to do is I'm trying to remember, like, actually I'm not even trying to, well, kind of trying to remember what we did in the previous example, but I'm also trying to like use logic here, that so that I'm not just trying to memorize what was in the code previously. I'm trying to think logically that, okay, what are we trying to do? Um, okay, it mentions here, why am I sitting here and thinking? So for each task, print a message indicating which task it is. Okay, so let's say task O1 is starting, and then we call sleep um, time sleep as, let's say, tk underscore sleep. Okay, tk underscore sleep, uh, duration from, you know what, let's do like let's do multiple seconds here instead of milliseconds. Actually, we could, yeah, no, let's do 1 second, 2 second, and 3 seconds. So that's our sleep duration. Then print a message indicating that it's done. So after it's done, we want to say task O1 is done, and optionally return a simple value like an I32. Okay, so in this case, it'll return an I32. There it is. Join handle, so and so. I need to see if there's a shortcut to add the type. Is there like a code action that I could take maybe? Let's do CA code action, no actions available. Okay. Source action, no actions available. It's hinting, but like, okay, whatever. Either, oh, what just happened? That wasn't supposed to happen. Okay, let's try that again. Join handle. I32, and it's gone again. That is odd. Why why is that happening? Hold on, I need to understand this. So join handle. Yeah, it seems to be overwriting some of the characters here. That's okay. Um, I can look into that later on, like why that's happening. For now, just join handle. This is system thread. No, I'm looking for this join handle. Somehow this join handle didn't overwrite the thing. Anyways, now I think I can just copy this and paste it. Okay, okay. So then we do task O2 and task O3. Here we do task O2. Okay, this one we can make it wait for actually. Hold on. Aren't we supposed to await this as well? I just remembered that we need to await these tasks. Like that's what actually that's what actually, gives the control back. So for task one, we can make it wait for 2 seconds. Task two can wait for 1 second, and then task three can wait for 3 seconds. Oh, actually, we could make task three wait for milliseconds. So we can make it wait for half a second. Yeah. Okay. Right. And here we can do, actually, here we can do 41, 42, and 43. So this way we'll know which task it came from. Okay, so then we collect the join handles for each spawn task. After spawning all the tasks, print a message from main indicating that all the tasks have been launched. Then await all the join handles in main to ensure. Wait, we have to await the join handles as well? That's I feel like I forgot that part. Yeah. I feel like I'd forgotten that part. Do we have to await the join handle words? Do we have to await the join handles as well? Await all the join handles in main to ensure all the tasks complete before before main exits. We have to await the join handles in order to make sure that the tasks complete. Okay, now I get it. Because I'm the most async programming that I've done has been in C sharp using the tap model. And in the tap model, I there was a similar kind of situation where you would have to store some kind of handle to a task and then await that. Eventually, like when you're trying to get the result of something, you would have to await the thing. And if the operation is not complete, then at that point you're going to be stuck awaiting it. Otherwise, if you just don't await it, if you just if you just let the thing carry on, if you let the program carry on by itself, the the program will it'll or rather the whatever is handling the async runtime, it's going to transfer control back to the main function, and the program will just continue executing as it is, um, and eventually the program will just exit, regardless whether your task is complete or not. Okay, so then let's create results. Result one equals task or one. Actually, wait, wasn't there something else that after spawning print a message indicating that all the, okay, yeah, let's print line, all tasks launched. Then let result o1 equals task o1 dot await. And then there was also the expect thing, which I'm guessing is for panicking. Returns the contained OK value, consuming the self value. Because this function may panic, its use is generally discouraged. Instead, prefer to use pattern matching and handle the error case explicitly, or call unwrap or else, or unwrap or default. Okay, all right. Wait, so then what just happened here? Okay, what would await do? Suspend execution until the result of a future is ready. Awaiting a future. What? Okay, hold on. Oh God, what just happened? Okay, yeah. Um, let's get rid of this and see what it's giving us. It's just giving us the result, isn't it? Yeah, I think it's just giving us a result. So I need to have a conversation with Gemini about this thing, like what would be the difference between just using await and await is a keyword from, wait, let's read this. Await is a keyword from the 2018 edition onwards. It's available for use in stable Rust from so and so onwards. Okay. Yeah, I need to have a conversation about like what would be the difference between these two, because like with expect, I kind of get it. Like it would still return. Oh, wait a minute. No, no, no. Hold up. This is not returning the value. I just realized that it's returning a result. It's returning a result. So the result could have an okay or an error. So then in order to get the value out of it, I would need to use something like unwrap or a match kind of thing. So I could do match this and then okay, um, I don't know, let's say I, and then we would print out the value using this, right? If it's an error, then just a second. I just want to make sure that this, like my understanding of this is correct, that this is exactly what what would be happening. Because like that expect line is a much more concise way to handle things, but like it's not always the best thing to do. Stuff like expect and unwrap, and I think there's a couple of other functions that they're good for debugging, they're good for getting results quickly. But if you're doing something that's meant to be production ready, that's meant to be used in production, then you definitely don't want to be adding in code that's meant to panic. You want to elegantly handle as many as many of the errors as you can. Um, you don't want to get into situations where your program keeps panicking. Oh yeah, for a second I was like, wait, what was I doing? Right. Okay. Actually, I don't think these are necessary. And I think if I hit save, the formatter is gonna like it's gonna remove a bunch of these things because, oh, you know what? I guess I was wrong. The formatter, I was expecting the formatter to remove this. Yeah, I was. How are we meant to handle this? Is it like this maybe? Oh, that's how. Okay. So if it's a one-line thing, then we have to do that. If it's not, if it's a code block, then we don't need to do the comma. I guess not. Um, yeah, I guess not. But yeah, good to know. So let's get rid of this. Let's get rid of that, and then do that, that, and that, and there we go. Nice, clean, much cleaner way. Now I need to see if there's a more concise way of doing this, because expect panics. In this case, the program is not going to panic. Well, okay, I think there is a concise way. I think that's what unwrap or gets used for. Let's see what unwrap or does. And then there's unwrap or default as well. Where is unwrap or? Here. This returns a contained OK result or a provided default. Arguments passed to unwrap or are eagerly evaluated. If you are passing the result of a function call, it's recommended to use unwrap or else, which is lazily evaluated. Okay, what does this do? This returns the OK value or computes it from a closure. Okay, so you're computing the value from like an anonymous function if OK is not returned. Okay, I'm going to need to explore these functions later on. I think I need to do much more stuff with. Dude, you know what? I never actually finished that Rustlings course. I need to go back into Rustlings. Though I think if I remember right, one of the reasons why I stopped with the Rustlings course was, or the Rustlings, what do you even call it? The Rustlings. It wasn't a course that I was doing. It was like a uh, what do you call it? It's basically something that gives you problems to solve, Rust problems to solve. The Rustlings thing. I stopped doing the Rustlings thing, or I paused it because I had gotten to the point where it was going into topics that I didn't know about, and reconnecting. Hopefully, it doesn't break up the stream. It says we are live. Are we Okay. I hope we are able to survive the disconnect protection thing. Yes, okay, we survived. Awesome. Now give me a second here while I set this whole thing up again and reconnect. Oh, okay. Yeah, we are really struggling here. Holy shit, dude. This is crazy. This is crazy. I'm wondering if it might be my USB to Ethernet adapter because it's specifically this thing that disconnected. It was specifically this machine that disconnected, and this is one of the few machines where I'm using a wired connection. And like this is also one of the few machines where I do tend to have issues here and there. Right. Okay. Great. So, what more do we need to do? After spawning all the tasks, print a message. Okay. Then await all the join handles to ensure all the tasks complete before main exits. Print the results. Return oh, okay. Print the results. Okay. All right. Um, res O1. What did that just do? Wait, that's interesting. Hold on. No, hold on. What did this just do? I just hit Control D and it seems to be. What is Control D doing? I'm curious. Hold on. NeoVim, LazyVim, uh, insert mode, Control D. When used in insert mode, deletes one shift width of indent. Oh, okay. Uh, at the beginning of the line, the indentation is always rounded to a multiple of shift width. All right. Add key binding for insert mode. I should look into this. Yeah, I should look into this thing. Okay. All right. So we print. Okay. Task O2. What's the actually I'm curious about what the error is here. Oh, moved. Okay, use of moved value. So the thing has been consumed, so it's not. Okay. Right. So aside from this, oh wait, am I not awaiting this? I'm not awaiting this. Thank you for that. Yeah, okay, what's the warning? Hold on. I want to read that again. Unused so and so that must be used. Futures do nothing unless you await or poll them. Okay. All right. So that's what it was. All right. Great. So now we can run. Okay, okay, okay. Hell yeah, dude. Hell yeah. Awesome. Okay, we are done with that. Um, do our results look something similar? Launching tasks. Okay. All right. Yeah, it did say that the results may vary. Um, but yeah, actually, can I? No, I can't do that. That's fine. Okay, great. So, what's next? Chapter 3. Oh, wasn't there a question that I was gonna ask? Oh, okay. Yeah. Um, I have a doubt. What exactly is await returning? Um, when I'm awaiting a join handle. Also, expect seems to be a good method for quick coding or quick and concise coding, but because it can panic, I'm guessing it's not advisable to use it everywhere. What's a more elegant? I don't know if I spelled that right. Is it elegant or elegant? Uh, where can I test this out? Hold on. Do I have spell check enabled here? Let's hold on. Let's type elegant and then, okay, I've enabled spelling. Let me change the spelling here. Yeah, okay, that's an error. That's the correct spelling. Okay, elegant. Okay, all right, great. Awesome. So, what's a more elegant way to handle um, these kinds of situations? Give it a second. Let it do its thing because I haven't touched it since yesterday. Okay, there we go. All right. So, right, those are two excellent, very important questions that get to the heart of writing robust Rust code. You're right on both counts. What does await on a join handle return? When you await a join handle, you aren't getting the raw return value of the task directly. Instead, you get a result. Specifically, you get a result so and so, so and so. Okay. T is the type of the value that your async block returns. In our exercise, if your task returns an I32, then T is I32. Okay. And then join error is a special error type that tells you why the task failed to complete. The most common reason is that the task panicked. So the full flow is spawn gives you a join handle, and then handle.await gives you a result. This result forces you to confront the fact that a suspended task might not succeed. Okay, it could be cancelled or it could panic. What's a more elegant way to handle What's a more elegant way than accept? Your intuition is spot on. Using dot unwrap or dot accept, no, expect. Have I been saying accept all this time? Actually, it makes sense, right? Accept as an exception. But then that's because I'm thinking about it in terms of exception. Have I been saying accept or expect? I don't know. I'm fine. Expect. I just noticed that. Or maybe I did notice it previously and I was saying expect previously, but then there are certain situations like today where I just get confused and I start saying accept again, which means that even though now I'm learning that it's expect, I'm probably going to say accept again later on. Though I don't think that's going to happen if I continue practicing Rust and I'm often using stuff like unwrap and accept. There you go again, accept, expect. Um, as long as I'm practicing and continuously using stuff like unwrap and expect, hopefully I'll remember it. I don't know. Okay, your intuition is spot on. Using unwrap and expect is great for examples, tests, or situations where if something fails, you have no way to recover and want the program to crash immediately. It's a way of saying I'm absolutely certain that this will succeed, and if it doesn't, it's a critical bug. Okay, in most real world applications, you don't want a single failed task to bring down your whole server or program, which is kind of funny to think about right now. Especially if you look up what caused the latest Cloudflare outage, people much more knowledgeable than me have made videos on this, but apparently an unwrap was what caused it because unwrap panics. So panicking means that the program is just going to crash. But okay, anyways, uh, where was I? Yeah, in most real world applications, you don't want a single failed task to bring down your whole server or program. The robust and idiomatic Rust way to handle a result is with a match block. Okay, so that's what I was doing previously. Well, that's what I'd spent some time doing earlier, and then I like erased it because, you know, this is an example, and we are fine with just doing expect. Um, Here's how you could rewrite the await part of our previous example to handle failure gracefully. Okay, dot await, and oh, this is basically what I did. Yeah, this is more or less what I did. Okay, why is this better? No panics. Your program doesn't crash if the spawn task fails. Explicit. It makes the success and failure paths explicit and easy to read. Then robust. It gives you a place to put your error handling logic like logging, retrying, or providing a default value instead of just giving up. If you only care about the success case and want to do nothing in the error case, you can use the slightly more concise if let. I completely forgot that this was a thing. I need to use this more often. I completely forgot that this was a thing. If let. I do not use if let nearly as often as I should. To be fair, I don't practice Rust nearly as often as I should, and I'm slowly practicing it more and more as I'm, doing more and more things with it. But yeah, dude, I'd completely forgotten that if let was a thing. Give me a second here. All right. Um, okay, great questions. This distinction is, wait, no, hold on. Let me read this again. If let, okay, and then that. Okay, all right. This distinction is fundamental to building reliable software in Rust. Now, feel free to try the Chapter 2 exercise, and you can even try using match to handle the results of your so-and-so. Let me know when you're ready to proceed. I'm ready to proceed. All right. Okay. Great. Holy shit, there's so much in this chapter. Oh my God. Oh God, it's still go. Okay. All right. We have a lot to get into here, so let's begin. All right. With the basics of spawning tasks understood, let's tackle a very common and important aspect of concurrent programming: how tasks communicate and share data. Okay, communicating between tasks. When you have multiple tasks running concurrently, um, they often need to share data or coordinate their actions. Doing this safely is a cornerstone of robust concurrent programming. Rust's ownership and borrowing rules combined with its type system are incredibly powerful and in preventing common concurrency bugs. Okay, um, right. The problem of sharing data between tasks. Imagine you have a variable, say a counter, and multiple tasks want to increment it. If they all try to increment it at the same time without coordination, you'll end up with a race condition where the final value of the counter is unpredictable and incorrect. In Rust, this problem is exacerbated by the ownership system. A value can only have one owner. If you try to pass a variable into spawn, the task takes ownership and your main function can no longer access it. If you try to borrow it, the borrow checker will complain that the task's lifetime is intermediate. It could outlive the main function's borrow. This is why move closures are often used with Tokio spawn. Move transfers ownership of my data to the task. Actually, okay, hold on. Um, okay, I guess we can get rid of all of this. Okay. Let's say A equals 5 and then B equals, I want to try and like do it like this. I have no idea what I'm doing here. But wait, let me see what this says. Captures a closure's environment by value. It captures a closure's environment by value. Move converts any variable captured by reference or mutable reference to variables captured by value. Data is no longer available. It is owned by the closure. Move closures may still implement fn or fn mute even though they capture variables by move. This is because the traits implemented by a closure type are determined by what the closure does with the captured values, not how not how it captures them. Okay, I did not get any of that. I'm gonna need to look that up later on and see. Hold on. Move is often used when threads are involved. Okay. Okay. Wait, so spawn takes what does so spawn can take an async block or an entire function, right? But the async block, what would the async block be considered? Because I don't think it's considered a closure like by default. Um, hold on, actually, let me try this. Let me see what this is returning. Say print line test. Okay, so this is returning a future where the output is unit type because okay, we can change that. Return 42. So now the output type is integer. Okay. Um, what was I gonna do? Yeah, move. I need to understand this thing about move. So this is our closure, right? In the closure we have this. So this works by itself. This works. Okay. What if we do let C equals A, right? Unused variable C. Now, A has been moved into this. I'm assuming that's what has happened. What if, hold on, what if I didn't do this? It's not throwing an error so far. Let's do print line and this and A. It's still not throwing an error. To be fair, um, what I'm using here is a what I'm using here is a type that implements the copy trait. So by default, it's going to copy, not move. Okay, what if I try um, a underscore str equals string new or string from? What does from return? From return string. Okay. Can I just give it any value? That works, right? Yeah, that works. Okay, now let's bring this in here. So far, we are good. What if I remove this? It's still not giving any errors. Though if I try to access this, um, okay, move occurs because this has so and so. It's not mentioning that the move occurred here. Where? Hold on. Borrow of moved value. It's not mentioning where exactly it got moved. This is where it's mentioning where it got moved. I I didn't notice there were 4 dots there. Okay. Variable moved due to use enclosure. If this is intentional, prefix it with so and so. Variable moved due to. Okay. I don't think I've created a decent example for this. Um, because like if it's getting moved anyways, then like what's the difference? I feel like I need to understand what. Dude, I just remembered I'd opened up this other Gemini instance. I'd opened this other Gemini CLI instance, and I forgot what I had opened it for. Pretty sure there was a reason for that, but I can't remember what it was. In the meantime, let me try. Okay, uh, this, okay. Right. While that takes its time to launch, actually, wait, did it launch? Okay, while it takes its time to launch, we can probably continue with this. Okay, so how do we allow multiple tasks, multiple tasks to safely access and modify the same piece of data? Arc mutex for shared state. This pattern is extremely common in both synchronous and asynchronous Rust for sharing multiple state, for sharing mutable state between threads or tasks. Let's break it down. Sorry, zoned out. Okay, let's break it down. T, this is the actual data you want to share. Okay, fine. Then mutex. This is a mutual exclusive primitive. Is that what mutex means? Mutual exclusion primitive. Okay, I've never explored this topic before, so I have no idea. This is a mutual exclusion primitive. It allows only one thread or task at a time to access and modify the data T inside it. When a task wants to access the data, it must lock the mutex. If another task already holds the lock, the current task will block until the lock is released. Important note. Mutex is blocking. While it protects your data, if a Tokio task tries to acquire a lock and it's held by another task, the current Tokio task will block, preventing the underlying OS thread from running other non-blocking tasks. For this reason, in async contexts, it's generally preferred to use Tokio Sync Mutex. Tokio Sync Mutex is asynchronous, and there's a difference between the mutex that's part of the standard library and the mutex that's part of the Tokio library. Okay, so this mutex is asynchronous and won't block the underlying thread. Instead, it'll yield control to the Tokio runtime. We'll use We'll use Tokio Sync Mutex here. Okay. Then arc, atomic reference counter. This is a thread-safe reference counting pointer. Arc allows multiple owners of the same data. When you clone an arc, you get another arc that points to the same data. Wait, okay. Sorry, I zoned out. Okay, when you clone an arc, you get another arc that points to the same data and the reference count is incremented. When an arc goes out of scope, the count is decremented. When the count reaches zero, okay, dude, I need to explore that. What the fuck was that? Smart pointers. I need to explore that smart pointers chapter, dude. Actually, I don't even know if arc is part of smart pointers. It should be because we have RC, which is ref counted. There's definitely box and ref cell. I don't remember if arc is part of that. I hope it's part of that. No, it's not a part of it. So we have box, RC, and then ref cell. I'm guessing RC is going to give me somewhat information close to what arc is supposed to be doing. Of course, they're probably not the exact same thing because if they were the exact same thing, then we wouldn't have two separate things, if you know what I'm saying. But yeah, hopefully exploring RC is going to give some good information. And I'm not sure where arc gets brought up. My best guess would be once we go into concurrency and we're doing shared state stuff, that's when it might get brought up. Yeah. Worst case scenario, I'll just fire up a new Gemini instance and I'll be like, okay, I learned Rust, but I never got a chance to learn about Arc. So let's learn about Arc. Okay, speaking of Gemini, my other Gemini instance launched. So I'm going to ask the question. What was the question? Oh, yeah. Okay. I'm learning about Tokio in Rust. We've reached a part where move is being used. Um, let's step outside the context of Tokyo for a second. I want to understand what exactly move does in this case. Keep in mind, I have um, very little experience in Rust. I'm still very much a beginner. So when you're giving examples, try to keep them simple. Okay, so while this is coming up with its answer, give me a second. Let me take a sip of my energy drink and hydrate and all that good stuff. Oh, sorry, zoned out for a second. Okay, so the answer that Gemini gave is a little bit long, so I might need to paste this into. Right, give me a second here. So I'm going to copy this and hopefully I'm able to drop it into something here. Wrong one. Uh, you know what? Okay. Okay, and let's do the wrap. I don't know if I have the markdown viewer or render markdown. I don't know if I have render markdown here. Actually, wait, let's quit this and uh, let's go back here and create a new thing. Gemini explains Rust move dot md. Right. Okay. Um. Oh, you know what we could do? We could open this up in Frogmouth instead. Yeah. Okay. So, of course, this is a fundamental concept in Rust, and it's a great question. Let's forget about Tokio completely and break it down. The key to understanding move is understanding Rust's core concept of ownership, the golden rule of ownership. In Rust, every value has a variable that's its owner. Crucially, there can only be one owner at a time. Think of it like a physical object. If I have a book, which is a value, and I am the owner, only I can hold it. If I let you borrow the book, you can read it, but it's still my book. I'll need it back. This is called borrowing in Rust using ampersand. I can give you the book. It's now your book. It's no longer mine. I cannot read it or do anything with it. This is called a move in Rust. Just a second. I just realized that something might be wrong here because this window seems to be out for some reason. I don't know. I don't know how long that's been happening. I'm not sure why that was happening. Well, I had to move it around a little bit previously, so I think that had something to do with it. Oh God, dude. I just realized something. This thing crashed. Give me a second. Give me a second here. Which one was it? I think it was this one that I need to launch. Yep, it crashed the uh when when my little connection issue was there. The whole thing crashed. I don't know how long it has been gone. I don't know how long the code has not been shown on screen, but I mean, it is what it is. It's crazy, dude. When if it's not one problem, it's another. If it's not another, then it's another. It's dude, it's wild. Hold on, is OBS still running over here? Let me just confirm. Yeah, the stream is still going. So OBS is still running here. Um, as long as the just a second. Let me make this do that, and then yeah, I think yeah, it's still running. It's still running. Yeah, we're still good. Just a second here. Okay. All right. The thing has launched. Let me just check OBS. Yes. Okay. We are good. Awesome. Now, back to this. Okay. What was I doing? Yeah, I was reading this. So let's see a simple example. No, what? Let's see it with a simple string. Right. So string implements move. It's not copy. So if you try to assign it to a different variable, then it's going to move the value. It's not going to copy it. So that's what happens here. S1 has the ownership of the string hello. We move the ownership of the string from S1 to S2, and S2 is now the owner. S1 owns nothing. Sorry, zoned out. Okay. Uh, yeah, S1 owns nothing. This next line would cause a compile error because S1 no longer owns anything. We can't use a variable after, no, you can't use a variable after you've moved it, after you've moved its value away. Okay, that makes sense. So what does move do with closures? A closure, or an anonymous function you can save in a variable, can use variables from its surrounding environment. By default, the closure will try to borrow the variables. Oh, you know what? I didn't know that. I didn't know that the default behavior was to borrow it. So like I would have, if I was writing a closure and I had to use an external variable like a surrounding value, then I would have tried borrowing it, not knowing that it's already borrowing it like implicitly. It's just looking at it. Okay. All right. Because the closure only borrowed name, we can still use it here. Name is still owned by the name variable in this function. All right. That makes sense. Then, forcing ownership with move. Now, let's add the move keyword. The move keyword before a closure forces the closure to take ownership of any outside variables it uses. Okay, all right. The move keyword forces the closure to take ownership of name. Okay, why would you ever need this? This becomes critical when you start dealing with threads, which is what Tokio manages. Imagine you create a closure to run on a different thread. That thread might outlive the current function. If the closure only borrowed, oh, that makes sense. Yeah, okay, the lifetime of the variable, it doesn't last that long. Doesn't last as long as the function in a different thread needs it. So then it would kind of become invalid. Okay, okay. If the closure only borrowed name and then the original function ended, the name variable would be destroyed. The thread would be left with a reference to memory that is no longer valid, which is a major bug, a dangling pointer. By using move, you are literally moving the data into the closure so it can live as long as the closure needs it, independent of the function that created it. TLDR move forces a closure to take ownership of the variables it captures from its environment instead of just borrowing them. Awesome. Okay, so that's done. We can remove this now. Awesome. So back to this. Okay. Sorry, zoned out. Okay, where was I? Mutex and then arc. Arc is essential because each task needs its own owned copy of the smart pointer to the shared data. If you didn't use arc, you couldn't move the same mutex into multiple tasks. Okay. Right. Putting it together. Arc mutex T. Wrap your data T in a mutex to ensure only one task can modify it at a time. Wrap the mutex in an arc to allow multiple tasks to share ownership of the mutex and thus the data inside it. So there's two things going on here. First of all, you want to make sure that only one task can actually modify it. So only one task can like I'm trying to think if this would count as a mutable borrow, but like it's not really a borrow, right? Because, well, I mean, could be a borrow, right? But yeah, okay. We have we want to make sure that only one task can modify it. So it can only be, it's mutable, but only to one task at a time. But at the same time, you want to allow multiple tasks to share ownership of it. But you don't want multiple tasks to be able uh, to modify it at the same time. At any given time, only one task should be able to modify it. And I'm guessing that's what mutex handles. And then arc makes it so multiple tasks can share ownership of that value. Okay. I'm gonna need some time to like go over this whole thing. Um, yeah, before I even like move forward, because there's multiple things here, right? There's introduction to channels, which is, it says it's a better way to communicate, while so and so is a great, no, while so and so is great for sharing state, often tasks don't need to share state directly, but rather messages or events. This is where channels shine. Channels provide a way for tasks to send data to each other. They operate like a queue. One end, the sender, sends messages, and the other end, receiver, receives them. The key benefit is that data is moved through the channel, adhering to Rust's ownership rules and avoiding direct shared mutable state, which simplifies reasoning about concurrency. Different types of channels exist: one shot for sending a single message, multiple producers, single consumer. Multiple senders can send to one receiver, most common for tasks sending data to a central processing task. Then multiple producer, multiple consumer. Multiple senders can send to multiple receivers. Broadcast, multiple senders can send to multiple receivers, and each receiver gets a copy of every message. Okay, right. Then we go into, hold on, we are specifically going into multiple producer and single consumer communication. Okay, so we are not exploring the others. So if, okay, what's in chapter 4? Let me just go back up. Chapter 4 is handling asynchronous IO. Asynchronous networking with NET, TCP listener, and TCP stream. Building a simple echo server, async file operations with so and so, and then exercise write a TCP client that connects to your echo server, sends a message, and prints the response. That should be interesting. Yeah, that'll definitely be interesting. And then we're going to explore sleep, timeout, interval, and finally managing multiple futures. The challenge of waiting for one of many events using the select macro to race multiple features. Okay. All right. All right. So I need some time to read this entire thing. Yeah. I need some time to read this entire thing, but give me a second here. Come study genetics with me. Okay, let's see what this person is doing. And then there's someone else here. PhD defense. PhD defense December. Ground truth and remote sensing. Slow burn Sunday. I am not sure what this person is doing. I hope, yes, okay, their thing is open, their chat is open. So we are going to go hang out there. Okay, so I'm going to start up the raid. Right. So that's going to be it for today's stream. Wait, I don't know if the raid thing started. I think my page is a bit glitched. So let me, okay, it is slowing down. Right. Oh, okay, there it is. Yeah. Okay, so that's going to be it for today's stream. I'm waiting for this stream manager page to load because for some reason my thing just went to shit. My internet connection, like everything is just all of a sudden not working. Okay, so I'm gonna unload that so we can get a little bit of bandwidth, and then I'm gonna reload this person's stream and my own stream manager. I think the raid is gonna go through anyways. I don't know if the raid is okay. The raid is going through. I hope you guys have a nice day, and I'll see you all next time. Peace.